Okay, so what I wanted to do in this video is to show you how I would analyze data so that you have a good sense of how to do this on the computer, because I know it's hard in the classroom. You might want to have this sort of, as a resource that you can use to see how I would do this from the starting point. So what I'm going to do is I'm going to share the screen. So let me just do that. I'm going to share, and I'm going to go to this data set right here. Um, What I have here is a data set that consists of 18 subjects who are male, female, ranging in age. Um, some of them are smokers. Some of them have had caffeine today or had not have caffeine. I have their systolic blood pressure. So that's the sort of when you have like 120 over 80, which is kind of a normal, that's what that represents. We have ethnicity, and we have the big five personality traits: openness to new experience, conscientiousness, extroversion, agreeableness, neuroticism, and then a quick IQ. It's actually a measure of emotional IQ. So I'm going to change this to um, quick emo IQ. Okay. And the way in which the scale works is that it is like an IQ test, with 100 being the average and standard deviation of 15, although this is in increments of 10. Doesn't really matter. But my point is that this is a typical data set. And what I really am going to do is I'm going to assign this to you all as uh, a data set for the homework assignment. So the first thing that we want to do is, of course, in any time that you have data like this, is you want to clean the data. Now, it's easy kind of to see where there are some errors in here. But the way in which I tend to do that is to go and create a pivot table. So I'm going to insert a pivot table, and I'm going to create a new table. And what I want to put in is different values. So in order to look at this, what I'm going to put in as a value is I'm just going to add subject number, because I'm not really interested in any of these um, data so far. What I'm really interested in is cleaning the data. So what I'm going to do is I'm going to put gender in under rows. Okay. And already I see there's a problem here. Okay. When I look at the sum of subjects, I have female, male, and then going back a value mallet. Okay. So that's an example of what you would want to do in order to clean it. So I'm going to go back here and I'm going to find mallet. Okay, and it's easy here because there's not that many to actually look at. But and I see right here that there's one where it should be male, but whoever was the research assistant may have entered that wrong, and I'm going to take that out. Um, and I go back to the pivot table, and it automatically changes it so that you can see it's now just male and female. Okay. Now, a lot of things can cause this problem. If you have capitalized letters, it'll look at it differently than lowercase letters. So you just need to be careful that all of your data is the same thing. So what I'm going to do is I'm going to get rid of gender, and I'm going to look at age. Okay. And I'm just going to put age in rows, and you can see already that there's a problem here. Okay, we have people that are 20, 25, 30, 35, 40, 50, 55, and someone who's 400 years old. Now, I imagine that 400 is a incorrect value. It probably is 40. And so what I'm going to do is I'm going to go back to the sheet, and I'm going to find the age of 400, and I'm going to change that to 40 and assume that that's the correct value. Now, you don't always have the ability to correct values like this. Oftentimes, it's the case that you might not know what the right answer is. And so, in that case, what I would suggest doing is to delete that value. Um, you know, Try to figure it out as best as you can. If it means going back to a survey that you handed out to people and you could figure it out through that, that could be one way of doing it. But doing it as a missing data is problematic, because then you again limit the number of observations that you have, and that can be problem. When data is scarce, you often need to figure out what's going on wrong. Okay, what about if I put smoker in here? Okay, that seemed to work here where there's yes and no's. But when I go back into this, I see that one of these is capitalized. I don't like that, so I'm going to make that lowercase. And then I'm going to go back to our pivot table. I'm going to take smoker out and I'm going to put in caffeine. Okay, so I'll put caffeine back here. And as you can see here, this is another common thing that'll happen. In a study where you have yes and no's, you might have someone spell out the word accidentally, or sometimes the spreadsheet itself will put in the wrong thing. So you want to get rid of that. So we're going to go back to sheet one and we're going to look where it says no, and that's right there. And I'm going to change that just to an N. Um, now, going back to the data, I'm going to say take out caffeine, and I'm going to put in systolic, put that in rows. And, what we have here is that, people down here have a very low blood pressure, and the people that have considerably high blood pressure, again, 120 is sort of the norm. And we have someone that's 1,200. You'd be dead if your blood pressure was that high. It's an impossible value. So what we need to do is to figure out like what's going on there. I would say that the best guess would be that it was meant to be 120. So I'm going to go back into my sheet and I'm going to make this one 120 so that it is a logical value for blood pressure. Okay. Now, what about this one here? Again, I think that it's always good to go back to our pivot table, take this out, and then put back ethnicity in. Okay, I'm going to put that in rows. And what we see is, again, a close look at this, we'll see that, at some point when someone entered the data, they misspelled Hispanic. This will often happen when you have people, subjects, write in their own responses. So you have to be particularly careful about that. And again, we go back to the data set and we look for that Hispanic that was incorrectly spelt, and we put it in the correct way. And once we go back to the pivot table, we can see that we only have our three categories anymore. Okay, now let's do it for these ocean traits. Okay, so I'm going to go back to the pivot table. I'm going to take out that, and I'm going to put O here. I'm going to add uh, O. And again, looking at this measure was a Likert scale on a scale of 1 to 8. Okay, so it's an even number scale. But look what we have here, 66. That clearly is not a correct value because it's way outside the range of what you would expect. My guess is that that meant to be a 6. So when I go back here and I find my 66, I'm going to change it to a 6. Okay, now let's see about these other ones. I'll take O out and I'm going to put in C. Okay, I'll add C there. That looks pretty normal. In this case, there's no one answered 1, but that's not unusual. That can happen when you have a scale like this. It seems like people were more on the upper side of the conscientious scale, apparently. Okay, let me add E. Okay, and E, we're missing 1, 2, 3, 4, 5, 6. We're missing 7. So in this case, most people answered in the midpoint of the scale. It can happen, but at least there's no values that are outside the range of what you would expect. Okay, I'm going to get rid of E. I'm going to put in A. Okay, and here we have, once again, 2, 3, 4, 5, 6, 7, 8, 9. That's relatively normal. And then let's put in N at the end. Okay, and here we have 1, 2, 3, 4, 5, up to 77. Clearly, 77 was an incorrect response, so I'm going to go back to my sheet. I'm going to see 77. Probably that was an error. And this can happen also when you ask people to type in a computer program like Inquisit, they could give an incorrect answer. So you want to correct that and make it be the one that you wanted. Now, I'm going to go back to the pivot table and do my last one and put in quick emotion. So I'm going to add quick emo scale. And as I told you, the scale is like an IQ test where, it has a mean of 100, standard deviation of 15. And we have values that, range. And then we have one value that's 1,000. Now, what I would argue is that that's way outside the range of what you could get on this test. I think that the highest you can possibly get is 300. So 1,000 is way outside the range. So what we need to do is to go back, find it, and I would assume that this was meant to be 100. Okay, and this, we've now cleaned our data. So what I'm going to do now is I'm going to import this into Jamovi. And what I'm going to do though is pause because I realize I don't have Jamovi open yet and I don't want to waste your time doing that. So I'm going to stop sharing and I'm going to pause. Okay, so I'm back and I think I have everything set up. So I'm going to share the screen and I'm going to go back to this and I'm going to do it the easy way of, uploading data by going and downloading this as a CSV file. And then I'm going to go over to Jamovi and it's called Supplementary Lecture. And I'm going to go over here and I'm going to open. And I'm going to go in the downloads, supplementary lecture. It should be right here. And I'm double clicking it and it is opening. And so now we have our clean data here in Jamovi. Why I like doing this is that it tends to look at the variables and put the names on the top automatically. But one of the things that it, as well as um, SPSS does wrong is that it often looks at some of these variables as being categorical when they're actually continuous. So what I need to do is to click on each of those that are numeric, and I need to change this from nominal to continuous. Okay, so I'll do that. This one, smoker, is yes and no. That is not continuous. So it's nominal, so I'm going to leave it that way. And I'm going to go over to systolic, that's continuous. So I'm going to go and I'm going to make that continuous. And I'm going to go to openness. I'm going to make that continuous. Conscientiousness, I'm going to make it continuous. Extroversion, I'll make that continuous. Agreeableness, continuous. Neuroticism, continuous. And the quick emotional IQ test, I'm going to go and make that continuous as well. And there we have our variables that are able to be analyzed the correct way. This is a step that most students forget to do. And I wanted to point this out because it's one of the reasons why people have frustration with Jamovi and SPSS, because they neglect to do this very simple part of the process. Okay, so what would you do first? Yeah, I think that, it might be useful to do some exploration. So I'm going to go and do explanation. I'm going to do descriptives. And let's say that I'm interested in, the quick emotion IQ score. I'm going to put that in variables, and it gives me the number of observation, the average, which is 102, the median, standard deviation, all of those good things. But let's say that I wanted to split that by gender to see if there is a relationship there. That gives me, the gender and the breakup. So the average for females is 96, for males it's 106. Um, I could also do it by, looking at the effect of if you're a smoker or not. So I can split by both of those. And of course, I can go down to plots and I can do anything from, I think a box plot might be interesting. So I'll go down there and see how that would produce it. And you can see that these are females, non-smoker, smoker, non-smoker, smoker, males. And this is a very quick and easy way of getting at that kind of data. You could also maybe do a bar plot. That's easy as well. Or you could even do a histogram, okay, which doesn't make a lot of sense in this context because you don't have a lot of data. But, if we were to take out gender and smoker, we could at least get a idea of what the, distribution looks like. It looks kind of like a normal curve, not perfect, but, good enough. And this is the overall average with the standard error bars put in. Standard error bars are, again, a useful way of looking at variability. And they are often used as a very quick way of being able to determine whether or not two distributions differ. So let me just put gender back in. And when I look at a standard error bar, if I take the top of this bar and I move it over here, and it intersects with the standard error bar over here, what that means is that there's not a statistically significant difference between the two groups. Okay. So if I were to pull this over like this, it looks like these bars intersect. And so I would be able to say that there's probably not a significant difference between females and males on this emotional IQ. Now, again, this is a quick and dirty rule that usually works when you have more than 10 observations in each group. It doesn't always perfectly work, but it's a useful heuristic to see whether or not these groups differ. If we really are going to do that, though, to see whether or not males and females differ, we have to run a t-test, okay? And in this case, it's going to be an independent samples t-test because we're running a comparison looking at different groups of people, specifically males and females. So I'm going to put male, gender, male and female as my grouping variable, and I'm going to put their score on the quick emotional scale as the dependent variable, okay? And what we have here is a statistic where the way that we would write this out is T equals negative 1.21 with 16 degrees of freedom. And the p-value is 0.24. So is this statistically significant? Well, the answer for you should be no, because this p-value right here is greater than 0.05. If it was less than 0.05, then we could say that it is significant. Um, let's test something else. We can take out quick emotion and let's see if there's a difference between gender and blood pressure. Okay. Once again, we have T with 16 degrees of freedom equals 0.149. Okay. P equals 0.88. Not statistically significant. Okay. So gender isn't. But let's look at something else like, smoking. Okay. Smoking tends to affect blood pressure. And so when we look at this, we find that T 16 equals 0.867. Again, not, statistically significant. So at least in this small data set, we're not finding an effect of smoking. Well, what about caffeine? Okay. Caffeine also doesn't seem to have an effect. T, 16 degrees of freedom equals 1.41. P equals 0.17. Okay, so what we're not really finding that there is, that many effects in this data set. Now, gender, um, caffeine, yes or no, smoker, these are all categories which are dichotomous that there's only two values. What happens when we have values that are more than just two? In this case, we have ethnicity, okay? And when I put it in here, it says grouping variable ethnicity must have exactly two levels. Why? Because if you remember from the spreadsheet before, the levels in ethnicity were white, black, and Hispanic. Okay. So because there's three of them, we can't run a t-test. We have to run an ANOVA. Okay. ANOVA allows you to run more than two groups. Now, of course, you can run an ANOVA with just two groups. And again, as I said in class, all that an ANOVA with two groups is the t value that you get is going to be the f value that you get with an ANOVA, but it's the square root. So, as I said, you don't really need to use t-tests at all, really. Although they're useful because when you have two groups, they're quite familiar to people and very easy to understand. So in order to do it when we have multiple groups, as an ethnicity here, we need to do a one-way ANOVA. So what I'm going to do is I'm going to put ethnicity as the grouping variable, and then I'm going to put systolic back in as our dependent variable, because let's say I'm interested in that. Now, in this case, what we have here is a f value with f, then brackets 2. Why is it 2? Because it's the number of groups minus 1. So 3 groups, the different ethnicities, minus 1 equals 2. And the second degree of freedom is 9.44. You might ask, why is that, a decimal point that you've never seen that before? That has to do with the fact that what modern statistics, we are able to calculate a value for a degree of freedom that's fractional in nature. Back in the day, years ago, we couldn't do it that way, but now we can. And what we're seeing here is that there's not a significant effect. Well, let's look at this using our exploration. So I'm going to go descriptives, and what I'm going to do is I'm going to put ethnicity that I'm going to split by. I'm going to put systolic here, and let's look at a bar plot, of these results. Okay. And what we're finding is that if we pull the value here over, it intersects with the value of this error bar and intersects with this error bar. So in this case, looking at ethnicity on systolic blood pressure, we're not finding that there's any difference. Well, let's look at something else. Okay, let's look at um, openness to new experience. Okay. So here, look at this effect. Okay. We have black down here, we have Hispanic up here, and we have white down here. Do you think that there's going to be a difference between one of these groups? In other words, is one of these doing something different than the others? Okay. And I would argue, yes, this middle group here, the Hispanics are much higher on this scale than either the whites or the blacks. Well, how could we test that using one of our tests of mean differences? Let's go back to ANOVA and let's do a one-way ANOVA and let's look at our grouping variable being ethnicity and our dependent variable being openness to new experience. Are you going to guess if the p-value is going to be significant or not? Look at this. We have an f value of f2, comma 10 equals 41.6. P is less than 0.0001 or 001. Sorry, I just got distracted by a text message. Um, so what this is saying is that there is a significant difference between the different levels of ethnicity and on openness to new experience. Let's try something different. Let's try conscientiousness. Okay. So I'll put conscientiousness in there. And look, once again, we have F2 9.52 equals 29. P is less than 0.001. Okay. So there is a difference in conscientiousness. Let's see what it looks like. We'll go to descriptives. We'll put conscientiousness in there and we'll split by ethnicity. Okay. And lo and behold, what we find when we do a bar plot is that one of these groups, again, is different than the others. Whereas the black respondents are, in this experiment, much lower than either the Hispanic or the white respondents. Now, an important thing that I want to point out here that you should, remember is that when you're doing a ANOVA like this, all that the result that we get here, these F values and, this P value right here, says that one group is different than one other group. Okay? It doesn't mean that all three groups are different than each other. It just means that one of them is different than one other. Okay? In order to determine which group is different from which other group, you need to do a follow-up test. So let's go back to ANOVA. We'll do a one-way ANOVA, and we'll put in ethnicity as our grouping variable. We'll put in conscientiousness here. And then down here where it says post hoc tests, we have to do the one, there's a couple of them, but the one that you want to usually do is Tukey. Okay. And again, most people around Thanksgiving said that it's Turkey's test, but it's actually a guy named John Tukey. And when you look at this, what this is saying right here, okay, this is the ANOVA and this is the post hoc. What this is saying is that it can't calculate the black group from the black group or the white group from the white group or the Hispanic from the Hispanic because they're the same group. But black and Hispanic, the difference between the means is 4.33. That difference is highly significant. Okay. Black and white, highly significant. Okay. That p-value is less than 0.004. Okay. But what about Hispanic and white? In that case, the difference is only 1.5. Okay, and you can see here, this p-value right there is not below 0.05. So what that means is that this is not statistically significant. Okay, so basically, when we look at this again, Hispanic and white right here are the same, whereas black and Hispanic are different, and black and white are different. Okay. Now, again, this is where that rule where if you draw this line over, it looks like it should be statistically significant. But again, when you look at these data, there's only 6 observations in each of these ethnic categories. Not enough to use that rule. But the point is I wanted to use a data set that was small in this case so that you could easily get your eyes around it and understand it better than if you were looking at a huge data set like the weather data set that has 47,000, observations on it. But the same things will apply. But, with that data set, the standard error bars are going to be very, very minuscule because you have so much data. That goes back to that whole thing that I was telling you about in terms of um, the study that showed that you were more likely to die if you went to the hospital with chest pains on the weekend than during the week. Sure, there's a statistically significant effect, but because there was 800,000 observations, it means that even a small difference would be statistically significant. And this is where the issue of effect size comes up. Okay. Now, in ANOVA, the measure of effect size is going to be something that is called partial eta squared. Okay. And I am not sure exactly where that is right here, but it is one of the ones which is usually underneath. It may only be when we do this ANOVA right here, of course. And we of course could just do the same ANOVA that one-way ANOVA. We could just do it this way. I'm going to put in what was it that we had? Ethnicity as my fixed factor, and I'm going to put conscientiousness as my dependent variable, and we end up um, having a F value of um, 18, F2 15 equals 18, P is less than 0.001. And then if we wanted to get the effect size, we can click on this, which is called partial eta squared, and what that's showing is that there's a pretty strong effect size. Okay, 0.70 is on the stronger side. But this is just one way of measuring, an effect size. Now, if we had tons and tons of subjects, if we had 47,000 observations, then this value is going to be very tiny, okay, because the effect size isn't small. Even if you have a very low p-value, because of the fact that what's going on here is that you are increasing the power of your test by having such a large number of subjects. Okay, so that's something that we need to keep in mind whenever you're doing this, is that effect size is equally important as your test of significance in a case like this. Okay, so this is a basic ANOVA. Now, you could ask, well, what if I don't want to just test ethnicity, but I want to put other things in there? Okay, well, we can do that here. We can add gender. Okay, and so now we're testing whether or not there's effective gender. And what this is saying is that no, there's not an effective gender. F112 equals 0.138, and the p-value there is 0.717. I hope that you're beginning to realize this rule of thumb is that when your f value or your t value is large, your p-value is very small. When your f or your t value is small, as in the case of right here or right there, your p-value is going to be big. It's going to be greater than 0.05, and so it's not going to be statistically significant. And you can see here, look at the effect size here. The effective gender in this case is very tiny because there's in fact no significant effect. So the effect size here is very minuscule. But we don't need to stop there. We could also put in the effect of whether or not someone's a smoker or whether or not they had caffeine. Okay. Now, the more that we do this, this has been a problem with some of this program is that um, uh, sometimes when you put in too many things, it doesn't really do well in calculating. So I'm going to take one of them out. And one of the other problems with this data set is that there's too little data. Okay, there's something in statistics called over-parameterization. When you have too many factors, okay, so in ethnicity we have three, gender we have two. Three times two is six. Okay, then if we add another factor, you see how this residual there is 12? So if we added something like smoker, okay, what we're finding is that it's beginning to do what this breakdown where it says NaN. And what's going on here is that in this case, there are too few factors. There's too few data to be able to run this analysis. This actually doesn't happen in SPSS. So this is a good thing about Jamovi. What it's basically telling you is that you're including too many fixed factors into your analysis of variance, and that can be a problem. Okay, so now if we had a ton of data, this wouldn't be as much of an issue. And when we don't have as many factors in there, okay, when we have in this case only six factors, that's less of a problem. But let's see if any of the other ones come up with a significant interaction so I can talk a bit about that. Okay, that one didn't. Let's see if extroversion did. Okay, and extroversion did. Okay, so what this is saying is that there is a differential effect of ethnicity and gender. How can we visualize that? Well, we can go back to our exploration and we can go to descriptives and we can put extroversion in this variables right there, and we can split by ethnicity and by what was the other one I had in there? Gender. So I'm going to put gender in there and ethnicity. And then let's create a bar plot, okay, where we look at this data. Okay. What this is saying is that, the effect is not identical between the different conditions. Okay, it looks it here, but what this is probably saying is that there's not an effect between these two conditions, but there is an effect with these other conditions. That may be because in this case, look how small that standard error bar is right there. There might not be enough variability in that grouping. Again, there's only 6 observations per group, so there's not a lot of data there. I'm going to take E out and let's put A and let's see what agreeableness looks like. Okay, so if I go down to the bottom here, look at this effect. Okay, there seems to be a really strong effect for Hispanics between female and male. Okay, you can see this big group difference here, but less so here. You see how this standard error bar intersects with this one, and then this one is in the opposite direction. And again, there is this intersection. So let's do this as an analysis of variance. So I'm going to go back to ANOVA. I'm going to go and I'm going to take A as our dependent variable. I'm going to put gender and I'm going to put an ethnicity. And what do you think is going to happen? Is there going to be an interaction effect? Looking at this data right here, I want you to like reflect on that for a second, whether or not you think there's going to be an interaction effect or not. Remember, an interaction effect is simply showing that, when you have different groups, that they don't all show the same pattern of results. So are all of these showing the same pattern? I would say no. So I want you to think about that for a second, and then I will, hit. Um, okay, I'm going to put ethnicity in. Boom. Okay. And look at this. There is an effect of ethnicity in general. When we compare this group to this group to this hut group, there is a difference of ethnicity. But this interaction effect actually isn't significant. It's just marginally significant at 0.09. Again, these things are hard to visualize. This is why we run ANOVAs and things like this, is because these are hard to visualize on their own. Okay. So that is sort of the idea behind what, our basic ANOVAs are. What I might do is pause this video so that it's not too large for you to have to watch, and then start a new one, just to make sure that all of this is working. Okay, so I'm going to stop sharing and I'm going to stop recording, and I'll see you in the next video.